till several months, and which is about the possibility that long period pulsars can be outcomes from fallback from supernova, from which they form. And we have worked on this with Nanda, Vanessa, and also Natasha Woolley-Walker, which is a researcher in Australia at the University of Perth. And she basically was the trigger for this work. And I will tell you why in a few seconds. So first of all, there was this discovery. Let me move this if I can. Yes. Okay. There was this very mysterious discovery this year about a very unusual radio transient, which was discovered in this survey, which is called the GLIMX, which is a survey that has been done in 2018, and was a radio survey that was planning to survey basically all the galactic plane in radio. And this source has been discovered here, near the galactic disk. And what was weird about it is that it has a very long periods, about 18 minutes periods showing pulsation every 18 minutes. And of course, we don't know exactly what it is. There is still work doing on this mysterious source. And this was discovered in a very low radio band, around between 70 and 200 megahertz. And here you can see some features of this of the emission of this source. So this is the detection of the pulses that have a very spiky and variable pulse shape all over the period where it has been observed. And also the fluxes, which are here, and the fluencies as well, show like a burst shape where the intensity of radiation goes up and then goes down very slowly in time. And so it seems that like that the radio emission of this source is triggered by an outburst or something. And the interesting thing is that it is linearly polarized, the radiation coming from this source. And well, the period is very long, and there is no very good indication on the period derivative. There is an upper limit, and so we don't know if this source is what is doing right now, but it seems to spin down. So the period is increasing in time a bit. And the luminosity, given the distance of the source, which is around 1.3 kiloparsecs, and the flux, which is around 40 Jansky, translating to a very high luminosity, around 10 to the 30 erg per second. So we can like put this source inside this this plane. This plane show the this plane show the luminosity in radio versus the width of the radiation emitted of the from sources multiplied by the frequency in radio. So for simplicity, you can think about this axis as being the pulse width of these sources, which is an indication also of the compactness of the source emitting. So you can see here that basically there are two parts in this plot. There is a part in the lower right corner, which is given by sources that have an incoherent radiation, basically, which is indicated by having low brightness temperature. The brightness temperature indicates how intense is the radiation and how compact is the source. So if the brightness temperature is very low, under 10 to the 12 Kelvin, usually, you expect the source to be incoherent and maybe to emit thermally or to emit any kind of incoherent radiation. If the brightness temperature increase, the intensity of the radiation becomes higher and higher, and you expect the source to emit coherently, so like a laser beam, basically. And here, in this part of the plane, you can see the normal radio pulsar, basically, and some giant pulses from neutron stars, some magnetars emitting radio, the fast radio burst as well, and our source, the glimpse source, is here. And the pulses are here depending on if you take like the variability time scale as an indication of the width, or the entire pulse width. And so what we can get from this plot is that the sources that emit coherently seems to be produced basically by sources that are highly magnetic, like neutron stars, for example. And while the other ones that emit incoherently have a lower magnetic field, usually. So, and this could be an indication that also this new source can be produced by in a highly magnetic environment. So, for example, magnetosphere of a neutron star or this kind of objects. Okay, apart from this, what are the indication of neutron stars with very long periods? So there was 30 years ago the discovery of this object, which is was discovered in a supernova remnant, and this is a very young supernova remnant with around 2,000 years as an age and a distance of 3 kiloparsec, more or less. And this object is a very compact source at the center of the supernova remnant emitting in X-rays. And in 2006, it was basically affirmed that this source has a modulation, a period, which is around 6 hours long. So it's a huge period if you think at something that is spinning and it is so compact. And also, apart from this, in the this source has undergone a couple of outburst episodes in X-rays, where the luminosity in X-rays has increased a couple of times, reaching 10 to the 35 erg per second. And this basically is an indication that we are in front of a highly magnetic star, like a magnetar, with a field that can be high as 10 to the 14 Gauss. So this is believed to be a neutron star right now. So let's put everything together, more or less. This is the usual plot for neutron stars, where you plot the period derivative versus the spin period. And you have the bulk of neutron stars, the isolated one, and the one in binaries that are milliseconds pulsars. You have the magnetars here. And you have this new source, the GLIMX, and the very long period neutron stars that I just show you here. So they are very detached from the rest of neutron stars. We don't know if this is a neutron star, but if we plot together with the other one, we can see that there is something going on here. So the evolutionary scenario for, let's say, normal isolated pulsar is that they are born from a period which is around a few tens of seconds, sorry, a few milliseconds to some tens of seconds, yes, and they spin down due to electromagnetic torque and electromagnetic radiation, and can reach period till a few seconds for the magnetars. If these are neutron stars, we have to expect that there is or another scenario for their formation. So maybe in the supernova where they are formed, they can be formed with a higher spin period from the beginning, or maybe there is a different evolutionary scenario for these sources. So what are the possible way to spin down a neutron stars to very long spin period? Well, the simplest way is to spin down via electromagnetic torque, which is the normal way usually neutron stars spin down. And I will talk later about it a bit. And the second way is the spin down due to interaction with the neutron star interact with a disk external to the neutron star. that exerts a torque on the central object, and so is able to modify the period and the period evolution of these objects. And other theoretical works have shown that there is another way, possibly, especially for highly magnetic stars like magnetars, which is an enhanced spin down due to winds that are produced when the magnetars emit very high energy outbursts of radiation, and that should be due to rearrangement in the magnetosphere and in the magnetic field that can cause reconnection and expulsion of winds of charged particles. And if those winds act, they can expand the open flux lines of magnetic field, and so enhance the spin down, the electromagnetic spin down of the neutron star for a while. And if a lot of such outbursts occurs during the lifetime of a neutron star, you could expect that the neutron star can span down to some very long periods. But I will not talk in detail about this. I will concentrate on the first two mechanisms, basically, and compare them. So let's start with the normal electromagnetic polar torque. So the usual picture of a neutron star is that it has a magnetic field, it has a dipolar magnetic field, and if you have a magnetic dipole spinning, you expect it to lose energy, so to spin down, emitting electromagnetic radiation. And in a different way, you can think about it that the magnetosphere around the star exerts a torque on the central star, and this torque spin down the central star. And this torque is usually proportional to the flux of open magnetic field lines that are over here. There is a distinction between open magnetic field lines and closed magnetic field lines, which is dictated by the fact that the magnetosphere of the neutron star rotates with the star itself at the same period. And if you go far away from the star, of course the speed should increase, and at some point you reach a limit, which is the speed of light, where the magnetic field and the magnetosphere can co-rotate with the star, and so the field basically open up. The magnetic field lines opens up, creating these open magnetic field lines going to infinity, basically. And this place is also where the radio emission from neutron stars is believed to be generated. Radio emission is believed to be generated in accelerated particles that emit radiation due, for example, to potential gap in the magnetosphere that create the electric field that can accelerate to very high energy the particles that can emit in synchrotron since they are in magnetic field, and so on. But the emission for the radio is still not very understood till now. So this is a way to spin down, but if we try to extend this way of thinking to very long period neutron stars, like 10 to the 3 seconds, like the gleam source, or if we think also to 6 hours long periods, we can see that there is something that is not working. So in this plot, I show the period as evolving time according to the usual spin down formula, which is over here, which depends on the magnetic field strength. And there's a dependence, of course, on the moment of inertia of the star, the inclination angle between the magnetic field and the rotation axis. We can introduce some correction factor, but it's only an order of magnitude at most. And on top of this, we expect also the magnetic field of a neutron star to evolve in time, because you have a magnetic field that is basically threatening the star, and the magnetic field is expected to decay in time according to two effects, which are the Hall effects and the ohmic dissipation. So what the Hall effect does is to redistribute the magnetic energy in the star to lower scales, and to enhance the ohmic dissipation, so the dissipation of currents in the neutron star crust and so on. So if you think of the magnetic field dissipating in the neutron star crust only, so of a neutron star where the magnetic field is permeating only the external layers of the star and not the core, you expect the evolution of the field to follow a sort of exponential decay in time, which is regulated by two time scale, the old time scale, which is around 10 to the 3, 10 to the 4, and depends in years and depends on the intensity of the magnetic field, and the ohmic time scale, which is basically the Ohm dissipation effects, which instead do not depend on the magnetic field, and there's a scale of around 10 to the 6 years. So if the magnetic field decay exponentially, you expect the torque exactly on the star to be strong at the beginning. So where you can see the curve here that are increasing the period depending on the strength of the magnetic field. If the magnetic field is very strong, the torque is very high, so the spin down is faster. But at some point, when the magnetic field goes basically very low in strength, the torque ceases to be effective. And this is why you reach a plateau at some point, where the magnetic field basically is not anymore exerting a lot of torque on the neutron star, and so the period stabilizes. And here is the bulk of pulsars that we have detected so far. These are the magnetars, so the ones that are very magnetic, with the magnetic field that ranges between 10 to the 14, 10 to the 15 Gauss. And as you can see, there is nothing over there for the neutron stars that have been detected. And also, if you predict an evolution for the spin down due to this formula only, together with the magnetic field, you predict to not reach periods that are larger than 10 to the 2 seconds. And it's very difficult to reach 10 to the 3 in even higher periods. A possibility is that the magnetic field does not decay like this. So maybe the magnetic field stay constant for longer times. And these are the track for constant magnetic field, for example, which is the limiting case. And so in this case, you could reach longer periods because the torque is higher. But again, you have to expect very high magnetic field, around 10 to the 16, 10 to the 17 Gauss, which is really highly not really reachable in neutron stars. So a way to keep the magnetic field a bit constant in time is to think about a magnetic field that permeates the core. If the magnetic field is in the core and is generated by the currents in the core, the core is not very resistive as the crust of the neutron star. So the currents can not dissipate in time and are able to preserve the magnetic field for longer times. But again, it's not sure that this scenario where the magnetic field permeates the core is feasible, because it depends on the microscopic properties of the core, if it is superfluid or not. So it's very complicated. Okay, what is the other scenario? Since the spin down and the normal spin down seems to not be super effective in reaching this very long spin period, the other scenario is a fallback from supernova. So what happens? All neutron stars are believed to be generated by the supernova explosion of very massive stars, between 8 and 25 solar masses, more or less. And after the supernova occurs, part of the matter that is ejected in the supernova can be still bound to the gravitational potential of the central object, and can begin to fall down again on time scales beginning on around a few tenths of seconds after the supernova explosion. Supernova 3D simulation have shown that this fallback show an evolution like this, where basically after a few tenths of seconds, the rate of fallback reaches a very high peak, around a fraction of solar mass per second of accretion, of fallback basically. And then it decays very fast in time according to a power law, which is -5/3. And if this fallback matter possesses some angular momentum, you expect also that as it falls down, it begins to circularize to form an accretion disk around the central compact object. And this can occur on a time scale which is determined by the viscosity of the matter falling down. And depending on the angular momentum, the matter can circularize at different radii. The typical radii are around 10 to the 8 centimeters from the source, 10 to the 9. And this temperature of the disk that is already that is formed is around 10 to the 6 Kelvin, more or less at the beginning. So in this time scale, you expect the disk to form, and then how it evolves in time. So the evolution of the disk still is has been simulated by several people starting from the 90s, and for fallback disk, there is a difference between normal accretion disk around stars that are fed by a binary companion, for example, because in a binary, of course, you have the mass that is every time replenished by the companion. So you expect the accretion flow to be continuous. In the fallback scenario, of course, after the fallback episode and after you have formed the disk, you don't expect the disk to be replenished by new matter. So the evolution that you expect is that the rate of accretion in the disk decays in time. And what can also distribute the angular momentum in the disk is the some magnetic hydrodynamic turbulence that is created in the disk that determine the viscosity of the disk and can translate the angular momentum and distribute it along the disk. And this is why also you expect the disk to expand in time, because angular momentum is distributed. And as you lose angular momentum, you expect to expand the disk in time. And the coefficient that we use for determining the evolution of the disk are determined by the viscosity, which is determines how the turbulence acts in the disk, and the viscosity depends also on the opacity of the disk, because if you have a disk that is a plasma, so is ionized, you expect the magnetic hydrodynamic turbulence to be very active because the magnetic field are coupled with the matter, and so the accretion to proceed normally. But if the opacity is low, so there is no real match between radiation and matter, the magnetic field can be decoupled at this time, and so you don't produce enough turbulence to produce viscosity, and so to produce accretion in the disk. In our simplistic model, we assume that also at the inner side of the disk, which is this inside radius, the accretion rate should not exceed the Eddington luminosity. So as you move inside the disk, you expect the radiation produced and the temperature to increase. So there is a limit where the pressure exerted by the radiation that is emitted by the disk is able to counteract the gravity that is trying to that is making the matter falling down towards the central objects. So if there is this balance, you expect to reach this limit of luminosity, which is the Eddington limit. And corresponding to this luminosity, you have a limiting accretion rate, which is around 10 to the 18 grams per second. And if I go back a second, okay, here you can see that in supernova simulations, the expected accretion rate ranges between 10 to the minus 6 solar masses and 10 to the minus 2 solar masses per second, which correspond to 10 to the 26, 20 to the 29 grams per second, basically. So in supernova fallback, you expect the accretion rate to be highly super Eddington in the first phases and then to decay in time. But in our simplified scenario, we assume that in the inner side, the accretion towards the central object is limited by the Eddington limit. So what happens when the disk form and how it interacts with the central objects? We have to take into account 3 critical radii. The first one is called the magnetospheric radius, and basically depends from the balance between the run pressure of the matter that is accreting towards the compact objects and the magnetic pressure that is exerted by the magnetosphere, the magnetic field of the neutron star. So where there is this balance, you find basically this magnetospheric radius, which depends on the magnetic field and inversely depends on the accretion rate. And we need to compare this radius with the other 2 critical radii. The first one is the light cylinder radius that I talked a bit before, is where the magnetosphere reaches the speed of light. So is basically the radius where the magnetic field open up in a normal neutron star. And we have to compare it with also the co-rotation radius. So this is the Keplerian radius, where the matter, a test mass that is falling towards the neutron star, is rotating with the same speed of the neutron star itself. So it's co-rotating with the magnetosphere of the neutron star, basically. So depending on the position of the magnetospheric radius with respect to the other 2, you expect the evolution of the neutron star to follow different scenario, different paths. So let's start from the first case. So in the first case, for example, here you have the co-rotation radius, which is always lower than the light cylinder radius, and is here. You have the light cylinder radius that define where the closed magnetosphere ends, and you have that the infalling matter, which is here, does not exert a run pressure that is sufficient to penetrate inside the closed magnetosphere. So it stays outside the light cylinder. And in this scenario, you expect so the central neutron star to behave normally, so to spin down by electromagnetic radiation as if it's not really influenced by the external disk. And it is also able to emit in radio, because the magnetosphere is unperturbed by the disk. So you expect also to the star to be emitting in radio. To model the torque exerted on the neutron stars in this scenario, you have to take into account the normal dipolar spin down, which is the one that I showed you earlier, plus this accretion spin down, which is the one exerted on the light cylinder by the disk, which in this case is not really effective because the disk is very far away from the star. So in this case, the fallback disk is confined outside the light cylinder, and the neutron star spin down mainly by dipolar electromagnetic losses. And this phase is commonly addressed as the ejector phase. Okay, now if we increase a bit the pressure of the accretion flow of the disk, the term describing the torque of the accretion increase in this case. So in this case, you have the run pressure to be sufficiently high to penetrate inside the magnetosphere. This causes some field lines to open up, first of all, and so the magnetospheric radius now is between the co-rotation radius and the light cylinder radius. And if this happens, at the boundary between the accretion flow and the closed magnetosphere, you have that the neutron star magnetosphere is still rotating at a rate which is higher than the Keplerian orbital motion of the matter. So since here in this region, the plasma should follow the dynamics of the magnetosphere, because the magnetic field is strong and it dominates the dynamic of the plasma. If the matter enters this region, it should follow the motion of the magnetosphere compulsorily. But since the magnetosphere is orbiting at a super Keplerian rate, basically here it finds a centrifugal barrier, because the rotation is so high that the centrifugal force is able to win over the gravity, and so you expect here to produce a wind of matter expelled by the disk, and this is why you call this phase as propeller phase. Also, another thing is that since the disk is penetrated and has perturbed the internal magnetosphere, you expect also that the particle wind influence the dynamics of the magnetosphere somehow, switching off the possible radio emission mechanism that is producing the normal radio emission from pulsars. This because if you have, for example, if the radio emission is produced by gaps where a potential is effective, if you have particles moving on, charged particles moving on in magnetosphere, you expect this particle to screen maybe these gaps, and so to switch off the possible way to accelerate charged particle in the magnetosphere, for example. And on top of this, you have that, so the accretion torque is higher in this, and also the spin down torque is a bit higher because you have opened up the magnetic fields lines. So if you remember, this torque depends on how many field lines are open. And so if you have more open field lines, you expect also the normal dipole torque to be more effective. And so in this way, when the fallback disk penetrates inside the closed magnetosphere, there is a centrifugal barrier that prevents the accretion to reach directly the compact star. So the matter is expelled, and the neutron star spins down a lot due to this propeller effect. Okay, if you have questions, feel free to ask. Okay, the third scenario is when the run pressure is very high and is able to penetrate a lot inside the magnetosphere. And in this case, the magnetospheric radius is lower than the co-rotational radius. So in this case, you don't have a centrifugal barrier, because here the Keplerian speed is higher than the magnetospheric speed at which the star is rotating. So there is no expulsion of matter, but once here, the matter can freely enter the magnetosphere and be dominated by the magnetic field lines. It slows down inside the magnetosphere and can reach the central star. And here you have direct accretion on the neutron star. And since the matter here is rotating at a faster speed than the central neutron star, what you get is that the accretion is spinning up the central star, because you have a torque which is positive in total. And again, you have the spin down torque to be bigger, because you have opened up a lot of lines in this case. So you have to counterbalance. You have a balance between the accretion torque, which is very high and tends to spin up the stars, and this spin down torque, which is still acting on the neutron star. But the most effective in this scenario is the accretion torque. So the end point is the neutron star is that it is spinning up by the accretion. Okay, so after this introduction, I can show you an evolution model. So in the first panel here, you have the evolution of the accretion rate in the disk. So this is the accretion rate in the disk as it evolves in time. And at the inner radius, so the inner radius which is connected to the central compact objects, you have the accretion rate to be limited by the Eddington limit. This evolution in the accretion rate translates in an evolution of the different radii, basically. So at the very beginning, assuming that the neutron star is born with 0.01 seconds, you have the corotential radius, which is very close to the neutron star, the like cylinder radius, which is close but more far away with respect to the corrotation radius. And since the accretion rate is limited by the Eddington limit, you have the magnetospheric radius that is beyond the like cylinder. So we are in the first case where the accretion is not affecting the star, and the star can behave as a normal pulsar, as a normal neutron star spin down by dipolar losses alone. But as the accretion rate evolves in time and decays, you have that the star starts to spin down due to dipolar losses here. So also the corrotation radius increase, get further away, the like cylinder radius as well. And at some point, you see that here, the like cylinder radius meets the magnetospheric radius. At this point, you have the accretion that enters the magnetosphere. And so the propeller phase begins. And the propeller phase translates in an evolution of the period, which is very fast. And the periods can evolve from a few seconds to almost 1,000 seconds in a very short time. And at the final stage, you reach a spin equilibrium phase, where the magnetospheric radius is equal to the corrotation radius. And this means that the accretion torque of the produced by the accretion flow is zero. The total torque exerted on the neutron stars is zero because the flow of matter is orbiting the star at the same speed of the magnetosphere, basically. So you have a balance here, an equilibrium. But if you take into account the decay of the magnetic field, you have that at some point where the magnetic field starts to decay, so around 10 to the 4 for such a high magnetic field, 10 to the 4 years, you have that the magnetospheric radius starts to decay as well because the magnetic field is getting weaker, and so the accretion flow is able to penetrate even further. And if the spin equilibrium persists, you have a slightly evolution towards a spin up again of the source, in principle, in the very last stage. And here I also show the inner radius of the disk, which basically corresponds to the like cylinder radius if the magnetospheric radius is beyond, and afterwards it corresponds to the magnetospheric radius if the accretion flow is able to penetrate, and the outer radius of the disk, which evolves in this way, which is not really important here. Okay, is it okay? Okay. Okay, now I try to do the same, basically spanning a few values for the magnetic field and initial accretion rate in the disk. And you can see here the evolution curves. So the first panel over here corresponds to a fixed accretion rate in the disk, which is 10 to the 19 at the beginning, gram per second. And for different values of the magnetic field, which are over here from 10 to the 12 to 10 to the 15. And basically here you can see that the star is not influenced by the disk. So the accretion rate is too low to influence the evolution of the period in this case. And so the star here spin down as a normal neutron star with the normal dipolar losses. If you increase a bit the magnetospheric, the accretion rate, what happens is that for the higher magnetic fields, you start to experience the propeller phase. So in this case, you have a dramatic increase in the period, for example. And this, if you move further on, you see that more and more values of the magnetic field allows to enter the propeller phase. Here, for example, you enter the propeller phase for all the values of the magnetic field. But as you can see, if you increase too much the accretion rate, you can't reach very high spin periods by this evolution. So the sweet spot is around 10 to the 22, 20 to the 27, 25 grams per second, basically, to reach a very long spin period. Here is basically the same, but this time fixing the magnetic field and varying the accretion rate. And again, you can see that for magnetic fields that are typical of normal pulsars, so 10 to the 11, 10 to the 12, you can't reach long spin period. But if you increase the magnetic field, the propeller phase allows to reach very long spin period. So this indicated that you should need a magnetar to reach very high spin period of the order of 10 to the 3 and maybe 10 to the 4 seconds. Okay, so let's apply this to these sources, in particular to the gleaming source, which is this plot over here. So what I'm showing here is the initial magnetic field of the neutron star versus the initial accretion rate of the disk, of the fallback disk. And what we are doing here is modeling the evolution for every combination of parameters, so for every value of the accretion rate and the initial magnetic field, and see which combination allow to reach a spin period of the one observed for the gleaming source, which is 1091 seconds. And this is the parameter range allowed to that allows to reach these spin periods. And the color represents the time, so the age at which the source reaches this spin period. So as you can see, it ranges between 10 to the 3 years, 10 to the 4, 10 to the 5, more or less, depending on the values that you have for the magnetic field and accretion rate. And the contour lines here represent the total matter accreted by the disk. So here, for example, you have 10 to the minus 6 solar masses in total in this period of time. The same can be applied to this source that has been studied a lot, and several works have tried to do basically the same thing. And what you can see here is that to reach 10 to the 4, 6 hours long periods, you need a super strong magnetic field, around 5, 10 to the 15 magnetic field, and actually a very moderate accretion rate, around 10 to the 20 grams per second. And the difference between these two sources is that this source is being detected only in X-rays. So in principle, there is no radio emission associated to this source. So you could expect that this source is still in the propeller phase. So it's still be affected by the accretion rate of the fallback disk. And this can be justifiable because this is very young, it's like 2000 years old. This source instead can be like the older brother of this one, where the accretion rate has stopped for some reason. So the fallback disk has become inactive for some reason. And at some point it has recovered the radio pulsation phase, where it acts as a normal pulsar. So this age computed here for this source can be considered as a lower limit on the age of the source, because it's the age where the star has exited the propeller phase. It reaches the period and is exiting the propeller phase to recover the ejector phase. So the normal spin down scenario. Okay, so how can we stop the accretion in a fallback accretion disk to recover the radio emission? Is not very clear, but there are some studies that indicate that, for example, during the propeller phase, so when the matter that is accreting find a centrifugal barrier, you could expect that winds expel a lot of matter from the accretion disk, and at some point, the simplest scenario is where the accretion disk gets completely depleted, so there is no any more matter to accrete, basically, and the stars recover its status of as a normal pulsar. The second scenario, which is a bit more complicated maybe, is that the disk becomes completely neutral. So the accretion is regulated by the status of the matter inside the disk. If the disk is ionized, if it is a plasma, the accretion can continue because there is enough viscosity to transfer angular momentum. But as the disk expands and as the accretion rate decays in time, the temperature in the disk also decreases, especially in the outer part of the disk. So at some point, the disk becomes so cold that it translates into a neutral. Matter starts to neutralize. So there is a recombination between free electrons and atoms. And this can occur at a temperature of around 10 to the 4, 10 to the 3 Kelvin. These are the curves of opacities for different composition for the disk. So when the opacity drops, it means that there is a recombination of free ions and free electrons. And if this occurs, a neutralization front propagates from the outer part of the disk towards the inner part of the disk. And at some point, the disk can be completely neutralized and the accretion rate can be completely stopped by this mechanism. And some studies have shown that this can occur on timescales of around 10 to the 3, 10 to the 4 years. So if this happens, what you expect is that at some point, the propeller evolution is stops because the disk gets neutralized and the star recovers the normal spin down, but at a period of 1000 seconds. So at those periods, the spin down is not really effective and the stars continue to spin at this period. So this is an evolution example starting from a magnetic field of 4 times 10 to the 14 and with this accretion rate. And you can predict also the energetics of this system. So you have the accretion luminosity that goes down as the accretion rate evolves in time, according to this. And when the disk is neutralized, it drops because there is no more X-rays emitted by the accretion process. This is the rotational power of the central neutron star. As you can see in the propeller phase, it decays a lot in the final stages, and especially when the disk gets neutralized, where it becomes super low. So again, this indicates that for GLIMX, if it is emitting a radio emission with 10 to the 31 erg per second, and you have a super low rotational power, the radio emission can't be powered by the spin down of the neutron star, but there should be some other mechanism that make the star to go in outburst and to produce this energetic radio emission. And this can be, for example, a strong magnetic field, which is justifiable if you have a starting magnetic field of more than 10 to the 14 Gauss. So you need a magnetar in this case. Now the last thing that I show you is a still work in progress. So here I show the luminosity of the accretion disk that goes down, but at some point you should be able in principle to detect the the radiation coming from the surface of the star itself, because if it is really magnetic, it should be also very hot. And if this happens, we should be able to detect some X-ray luminosity coming from the surface. Chandra has observed this source for around 10 hours, but it has not detected anything, basically. So we have only upper limit on this, and these upper limits are shown in these two plots. This is around 10 to the 30 arc per second, and these are different spectral model used to find these upper limits, and this uncertainty depends on the certainty of the distance that we have. And so basically, we have an upper limit around 10 to the 30 arc per second for the luminosity in X-rays of this source. And if we try to translate this into and compare with other neutron star, so our source, the gleaming source, is over here with 10 to the 30 luminosity limit. This is the X-ray luminosity versus the characteristic age of the source. And these are other magnetars, other pulsars emitting where the emission of X-rays is visible. And on top of this, we have plotted some evolutionary curves of the surface of the luminosity of neutron stars from the magnetothermal code that is being developed in our group by Clara, Stefano, and Daniele for different magnetic field. So from 10 to the 15 and here 10 to the 12. And you can see that in the case of the magnetic field confined to the crust of the neutron star, strong magnetic field does not reach this region, because the temperature of the surface is so high that the luminosity should be detectable for this source, but it seems not the case. So a possible way out is to assume that there is some field that is threaded in the core. If the field is generated mainly in the core of the neutron star, it does not dissipate a lot in the crust because the currents are mainly in the core. So you expect the luminosity to be lower in this case. If this happens with these evolutionary curves for a core-dominated magnetic field, you could reach the lower limit, the upper limit of that has been detected for this source. So this is still work in progress. So and this could hint that we are in the presence of a very new source that maybe is the first time that we have a neutron stars with a core, with a evidence of a magnetic field that is threaded in the core, or maybe we are wrong. This is not a neutron stars and can be something else, but we still don't know. So I leave you with the conclusion. And yeah, if you have any further question, just let me know.
All right, we have time for a few quick questions. Any questions from the room first? Yes.
It's all very nice talk and very nice results. As an observer, I wonder if, like, okay, not in this case, but in another case, could we actually observe the fallback disk in like right after the supernova phase?
Okay.
Can you repeat
Yes.
the question?
So the question is if we can observe in some other case the fallback disk from the supernova. And so there are not evidence of disk around compact stars like neutron stars for now. There have been a couple of works claiming to have detected a disk around neutron stars. One that has detected like infrared emission possibly from a disk, but the results are like very few points, so it's not really super constraining. And another one that I don't remember well, but it should have observed some X-ray emission, possibly coming from a disk, but there are not super strong evidence towards this for now. So yeah.
Any more questions?
Yes. Hi. I noticed when you showing the interaction with the photodisk, that the axis, the relation axis, and the magnetic dipole axis were aligned.
Yes.
So, is it too difficult to simulate any other orthogonal case where there's misalignment, or
Okay.
have you thought what would be the difference in the results?
Okay. So the question is that in our model we use a magnetic field which is aligned with the rotation axis and the disk as well. If it is difficult to simulate a misaligned magnetic field, and if we have tried to do this, so the answer is no, we haven't tried to do this, and it's not really very easy, especially for a simplified model like this. In principle, if you have a misaligned magnetic field, you break the geometry. So you expect that the accretion flow behaves in a different way, interacting in a different way with the magnetosphere, because towards the pole, the accretion flow is able to penetrate more.
Right.
So, of
And
course,
you have like an intermittent accretion.
Yeah.
You can model it with like modulating the accretion at some point.
yes.
I don't know.
Yeah. Of course, we put ourselves in a very simplified scenario, and there are a lot of assumptions on it. But yes, it's something that could affect, of course, the evolution in general. Yeah.
Any final questions either from you or from the people online? Any things you want to know? Raise your hands or write in the chat. Don't think anyone is writing. Okay, good. Then let's thank Michele again for the seminar today. And then I hope there's pizza outside. Yeah. We have to leave first.